Tonight, we're going to explore fascinating truths about the stars that fill our night sky. These ancient beacons of light have witnessed the entire history of our universe. And tonight, they'll guide you gently into sleep. Let your breathing slow. Allow your mind to soften and drift with me through the cosmos as we discover the quiet wonders scattered across the darkness above. Deep within the galaxy, hidden in vast clouds of gas and dust, stars begin their long journey toward existence. These immense regions are called stellar nurseries or star-forming regions, and they contain everything needed to create new suns. The clouds themselves are composed mostly of hydrogen and helium, the simplest and most abundant elements in the universe, mixed with traces of heavier materials left behind by generations of stars that came before. When you look at the night sky, some of the faint patches of light you see are not individual stars at all, but entire nurseries filled with stars being born right now, their light reaching us after traveling for thousands of years through the quiet dark. Within these stellar nurseries, gravity works patiently over millions of years. Small disturbances in the cloud, perhaps triggered by the shock wave from a nearby supernova or the collision of two clouds, cause regions of gas to grow slightly denser. Once this process begins, gravity takes hold of the denser material and pulls more gas inward. The clump grows heavier and heavier, and its gravitational pull becomes stronger and stronger. Over time, the cloud fragments into many smaller cores, each one destined to become a star. This collapse happens slowly at first, then accelerates as the material falls inward, compressing under its own weight. At the center of each collapsing core, the temperature begins to rise, and the journey toward becoming a true star has begun. As a cloud collapses, the object at its center is not yet a star. It is called a protostar, a stellar embryo that shines from the heat of gravitational compression rather than nuclear fusion. The protostar phase can last for about 100,000 years, during which the object continues to gather mass from the surrounding cloud. It glows faintly in infrared light, hidden from view by the thick cocoon of dust and gas that still surrounds it. The protostar is warm, but not yet hot enough for the fusion reactions that will one day power it for billions of years. It is a promise of light waiting to be fulfilled, a newborn sun still wrapped in the remnants of its birth. Eventually, the core of the protostar reaches a temperature of about 10 million degrees Kelvin. At this astonishing heat, hydrogen atoms move so fast that they overcome the electrical repulsion between them and collide with enough force to fuse together. This process is called nuclear fusion, and it transforms hydrogen into helium, releasing tremendous amounts of energy in the process. The moment fusion begins is called stellar ignition, and it marks the true birth of the star. From this point onward, the star will shine not from the heat of collapse, but from the power of fusion burning at its core. The outward pressure from this energy balances the inward pull of gravity, and the star enters a long period of stability. Once a star begins fusing hydrogen into helium, it enters a phase called the main sequence. This is the longest and most stable period of a star's life, during which it maintains a careful balance between the outward pressure of fusion and the inward pull of gravity. About 90% of all stars in the universe are currently on the main sequence, steadily converting hydrogen into helium in their cores. Our Sun is a main sequence star and has been for about 4.5 billion years. It will remain on the main sequence for another 5 billion years before the hydrogen in its core is exhausted. The main sequence is like the long, quiet adulthood of a star's existence, a period of steady light and patient burning. When astronomers look at stars, they notice that they come in different colors. Some shine with a blue-white brilliance, while others glow with a soft red or golden hue. These colors reveal the star's surface temperature. The hottest stars burn blue or blue-white, with surface temperatures exceeding 30,000 degrees Kelvin. Slightly cooler stars appear white or yellow-white. Stars like our Sun, with surface temperatures around 5,800 degrees Kelvin, appear yellow. Cooler stars glow orange or red, with surface temperatures as low as 3,000 degrees Kelvin. Astronomers use a classification system that organizes stars by these temperatures using the letters O, B, A, F, G, K, and M, from hottest to coolest. This system allows us to understand a star simply by observing the color of its light. Among all the types of stars in the universe, red dwarfs are by far the most numerous. These small, cool stars have masses between about 8% and 50% that of our Sun. They burn their hydrogen fuel very slowly, which means they can live for trillions of years, far longer than the current age of the universe. Because they are so dim, red dwarfs cannot be seen with the naked eye from Earth, even though they make up about 70 to 80% of all stars in the galaxy. The closest star to our solar system, Proxima Centauri, is a red dwarf, shining faintly just over 4 light-years away. These humble stars will outlive all others, continuing to shine long after giants and supergiants have faded into darkness. Our Sun is classified as a G-type main sequence star, sometimes called a yellow dwarf. With a surface temperature of approximately 5,800 degrees Kelvin, it emits light that peaks in the green-yellow portion of the spectrum, though to our eyes it appears white when seen from space. The Sun has a mass of about 1 solar mass by definition, and contains enough hydrogen fuel to continue shining steadily for about another 5 billion years. It is neither especially large nor especially small, neither particularly hot nor particularly cool. In the grand scheme of stellar diversity, our Sun is pleasantly average, providing stable conditions that have allowed life to flourish on Earth for billions of years. At the opposite end of the spectrum from red dwarfs are the blue giants, massive stars that burn with fierce intensity. These stars can have masses 10 times or more than that of our Sun, and surface temperatures exceeding 30,000 degrees Kelvin. Their tremendous mass means they fuse hydrogen at prodigious rates, burning through their fuel supply in just a few million years. Blue giants are rare because they live such brief lives compared to other stars. Many of the brightest stars visible in our night sky, such as Rigel in the constellation Orion, are blue giants or supergiants. Their brilliant light can be seen across vast distances, making them cosmic beacons that illuminate the darkness, even though their time is fleeting. The light and heat that stars produce comes from nuclear fusion occurring deep within their cores. In the core of a star like our Sun, hydrogen nuclei collide and fuse together through a process called the proton-proton chain reaction. 4 hydrogen nuclei combine to create one helium nucleus, releasing energy in the form of gamma rays and neutrinos. The gamma rays slowly work their way outward through the star's layers, taking thousands of years to reach the surface, where they are finally released as the visible light and heat we feel. This fusion process converts a tiny amount of mass directly into energy, following Einstein's famous equation. It is this process that has powered the Sun for billions of years, and will continue to do so for billions more. While stars like the Sun rely primarily on the proton-proton chain reaction, more massive stars use a different process called the carbon-nitrogen-oxygen cycle, or CNO cycle. In this process, carbon, nitrogen, and oxygen act as catalysts that help fuse hydrogen into helium more efficiently. The CNO cycle is much more sensitive to temperature than the proton-proton chain, so it dominates in stars with higher core temperatures. This allows massive stars to burn their hydrogen much faster than smaller stars, which explains why they live such brief lives despite having more fuel to begin with. The CNO cycle releases similar amounts of energy per fusion reaction, but occurs at a much higher rate when temperatures are sufficiently high. When stars fuse hydrogen into helium, they are creating new elements that did not exist before. As stars age and exhaust their hydrogen fuel, they can begin fusing helium into heavier elements like carbon and oxygen. The most massive stars continue this process, fusing carbon into neon, neon into magnesium, and so on, creating elements all the way up to iron. These heavy elements are forged in the cores of stars over millions of years. When massive stars eventually explode as supernovae, they scatter these newly created elements into space, enriching the interstellar medium with the building blocks of planets and life. The carbon in our bodies, the oxygen we breathe, and the iron in our blood were all created inside stars billions of years ago. In massive stars, fusion continues through progressively heavier elements until iron is created in the core. Iron is special because it sits at the peak of nuclear binding energy. Fusing elements lighter than iron releases energy, but fusing iron requires energy instead. When a massive star creates an iron core, fusion effectively stops. Without the outward pressure from fusion reactions, the iron core can no longer support itself against gravity. Within seconds, the core collapses catastrophically, triggering one of the most powerful events in the universe, a supernova explosion. The core collapse happens so quickly that it releases as much energy in a few seconds as our Sun will emit over its entire 10 billion year lifetime. While fusion inside stars can create elements up to iron, elements heavier than iron are forged during supernova explosions. When the core of a massive star collapses, it creates conditions of extreme temperature and pressure that last only briefly. During this intense moment, neutrons are captured rapidly by atomic nuclei in a process called the R process, creating heavy elements like gold, platinum, and uranium. These precious metals that we mine from Earth's crust were created in supernova explosions billions of years ago, before our solar system even existed. Every gold ring, every silver coin, every uranium atom on Earth is the remnant of a stellar catastrophe, scattered into space and later incorporated into the cloud that formed our planet. After a massive star explodes as a supernova, what remains depends on the mass of its core. If the core's mass is between about 1.5 and 3 solar masses, it will collapse into a neutron star. Neutron stars are incredibly dense objects, typically only about 20 kilometers in diameter, but containing more mass than our entire Sun. A teaspoon of neutron star material would weigh about 1 trillion kilograms on Earth. If the core is more massive than about 3 solar masses, not even neutron degeneracy pressure can stop the collapse, and the core continues to shrink until it becomes a black hole. These stellar remnants represent the final stage in the life of the most massive stars, compact objects that continue to exist long after their fiery deaths. Stars with masses similar to our Sun follow a different evolutionary path. When they exhaust the hydrogen in their cores, they expand into red giants, then shed their outer layers as planetary nebulae. What remains is the hot, dense core, now called a white dwarf. A white dwarf is typically about the size of Earth but contains about half the mass of the Sun. These objects are supported not by fusion or ordinary gas pressure, but by electron degeneracy pressure, a quantum mechanical effect that prevents electrons from being squeezed too close together. White dwarfs do not generate new energy. They simply cool gradually over billions of years, slowly fading from white to red to black as they radiate away their remaining heat. The main sequence phase, when a star steadily fuses hydrogen into helium in its core, represents about 90% of its total lifetime. This is why when we look at the stars in the sky, most of them are main sequence stars. They spend relatively brief periods as protostars, then much briefer periods as giants or supergiants after exhausting their hydrogen. For a star like our Sun, the main sequence lasts about 10 billion years, while the red giant phase lasts only a few 100 million years. More massive stars have shorter main sequence lifetimes, but still spend the bulk of their active lives fusing hydrogen. This long, stable period is what makes stars such reliable sources of energy for any planets that might orbit them. The more massive a star is, the shorter its life will be. This might seem counterintuitive, since massive stars have more fuel, but they burn through that fuel at enormously higher rates. A star with 10 times the mass of the Sun will live for only about 10 to 20 million years on the main sequence, while our Sun will live for 10 billion years. Conversely, a red dwarf with only 10% the mass of the Sun can burn steadily for 10 trillion years or more. This inverse relationship between mass and lifetime means that the most massive stars we see in the sky are actually very young, having been born only a few million years ago, while the smallest red dwarfs born at the beginning of the universe are still in their infancy. When a star like our Sun exhausts the hydrogen in its core, it enters a new phase of life. The core, now composed of helium, begins to contract under gravity. As it contracts, it heats up, and this heat causes a shell of hydrogen around the core to begin fusing. The energy from this shell burning pushes the outer layers of the star outward, causing the star to swell to enormous size. The surface cools as it expands, giving the star a reddish color. This is the red giant phase. A star that was once the size of our Sun might grow to engulf the orbits of the inner planets, expanding to 100 times its previous radius. Despite this dramatic change, the red giant phase is relatively brief, lasting only a few 100 million years before the star moves on to its next evolutionary stage. As a red giant's helium core continues to contract, it eventually reaches temperatures of about 100 million degrees Kelvin. At this point, helium fusion can begin through a process called the triple alpha process, where 3 helium nuclei combine to form carbon. In stars with masses similar to our Sun, the core has become degenerate, meaning the electrons are packed so tightly that quantum effects dominate. When helium fusion finally ignites in such a core, it happens suddenly and explosively in what is called a helium flash. The entire core ignites almost instantly, releasing enormous amounts of energy. Paradoxically, this flash is not visible from outside the star because the energy goes into lifting the degeneracy and restructuring the core rather than increasing the star's surface brightness. After the helium flash, the star settles into a new period of stability, burning helium in its core while hydrogen burns in a shell around it. The most massive stars eventually evolve into supergiants, the largest stars in the universe. These immense objects can have radii hundreds or even over 1,000 times that of our Sun. If a supergiant like Betelgeuse were placed at the center of our solar system, its surface would extend beyond the orbit of Jupiter. Despite their enormous size, supergiants are not particularly dense. Their outer layers are so diffuse that they would be considered a near vacuum by Earth standards. These stars burn through multiple stages of fusion, creating layers of different elements like an onion. They are among the most luminous objects in the galaxy, shining with the light of hundreds of thousands of suns, which is why they can be seen across such vast distances. Not all stellar objects successfully become true stars. Brown dwarfs are objects that form like stars, collapsing from clouds of gas and dust, but never accumulate enough mass to achieve the core temperatures necessary for sustained hydrogen fusion. The dividing line between a brown dwarf and a true star is about 8% the mass of our Sun. Below this limit, the core never reaches the 10 million degrees Kelvin needed for hydrogen fusion. However, brown dwarfs with masses above about 13 times that of Jupiter can fuse deuterium, a heavy isotope of hydrogen, for a brief period. These objects glow dimly from the heat of their formation, and from this limited fusion, gradually cooling over hundreds of millions of years. They occupy a fascinating middle ground between the largest planets and the smallest stars. Despite their solidity in appearance, stars are primarily made of plasma, a state of matter where electrons have been stripped from atoms by extreme heat. The core of a star is incredibly dense, but even there, the individual particles of matter are separated by relatively large distances on the atomic scale. If you could somehow remove all the empty space from a star like our Sun and pack the matter together as tightly as in an atomic nucleus, the entire Sun would fit into a sphere only about 10 kilometers across. Of course, such compression cannot happen naturally in a regular star, which is why stars appear so large. It is the combination of high temperatures and relatively low density that allows fusion to continue steadily for billions of years. Einstein's famous equation, EXmc2, tells us that mass and energy are interchangeable. When the Sun fuses hydrogen into helium, a small amount of mass is converted directly into energy. Specifically, the Sun converts about 4 million tons of matter into energy every single second. This might sound like an enormous amount, but the Sun is so massive that it has been doing this for 4.5 billion years, and still has enough mass to continue for another 5 billion years. The energy released by this mass conversion is what makes the Sun shine and provides the light and heat that sustains life on Earth. Every photon of sunlight that touches your face is a testament to this continuous conversion of matter into energy. When fusion reactions occur in the Sun's core, they release energy in the form of high-energy gamma rays. These photons begin a long journey outward through the layers of the Sun. However, the Sun's interior is so dense that the photons are constantly being absorbed and re-emitted by atoms as they travel outward. Each time a photon is absorbed and re-emitted, it changes direction randomly, following a path called a random walk. This process is so inefficient that it can take anywhere from 10,000 to 100,000 years for energy created in the core to finally reach the surface. Once a photon reaches the Sun's surface, it escapes into space and takes only about 8 minutes to reach Earth. The sunlight warming your skin today began its journey in the Sun's core long before recorded human history began. Like planets, stars rotate on their axes. Our Sun completes one rotation approximately every 25 days at its equator, though it rotates more slowly at its poles because it is made of gas and plasma rather than solid rock. Different stars rotate at vastly different speeds. Some neutron stars, the collapsed cores of massive stars, can spin hundreds of times per second. Young stars tend to rotate faster than older stars because they lose angular momentum over time through stellar winds and magnetic interactions. The rotation of a star affects its shape, its magnetic field, and the patterns of convection in its outer layers. In some extreme cases, rapidly rotating stars can be significantly flattened at their poles due to centrifugal force. Just as Earth has an atmosphere that extends into space, stars have stellar winds, streams of charged particles flowing outward from their surfaces. Our Sun's stellar wind is called the solar wind, and it consists of particles moving outward at speeds of hundreds of kilometers per second. These particles create the heliosphere, a bubble of influence that extends far beyond the orbits of the planets. More massive and luminous stars have much stronger stellar winds, losing significant amounts of mass over their lifetimes. Red giants and supergiants can lose entire solar masses of material through their winds before they explode as supernovae. These winds enrich the interstellar medium with elements created inside the stars, contributing to the ongoing cycle of stellar birth and death. When ancient astronomers looked at the sky, they noticed that stars appeared to have different brightnesses. They developed a magnitude system where the brightest stars were called first magnitude, and the faintest visible stars were sixth magnitude. Modern astronomers have refined this system into the apparent magnitude scale, which is logarithmic. A difference of 5 magnitudes corresponds to a factor of exactly 100 in brightness. Importantly, the scale runs backward. Smaller numbers indicate brighter objects. The Sun has an apparent magnitude of -27, while the faintest objects detectable by the largest telescopes have apparent magnitudes of around 30. Apparent magnitude tells us how bright a star appears from Earth, but it does not tell us anything about the star's true luminosity, because nearby dim stars can appear brighter than distant brilliant ones. To compare the true luminosities of stars, astronomers use absolute magnitude, which is defined as the apparent magnitude a star would have if it were located exactly 10 parsecs, about 33 light-years, from Earth. This allows astronomers to compare stars on equal footing. The Sun's absolute magnitude is about plus 4.8, which means it is actually a fairly modest star. Many of the stars we see in the night sky have absolute magnitudes far lower, meaning much brighter than the Sun, which is why we can see them despite their great distances. Stars like Rigel and Deneb have absolute magnitudes around -7 to -9, meaning they are tens of thousands of times more luminous than our Sun. The relationship between distance and brightness follows an inverse square law. If you double the distance to a star, its apparent brightness decreases by a factor of 4. Triple the distance, and the brightness drops by a factor of 9. This means that a very luminous star far away can appear dimmer than a much less luminous star that is nearby. For example, Sirius is the brightest star in our night sky, not because it is extraordinarily luminous, but because it is relatively close, only about 8.5 light-years away. If Sirius were moved to the same distance as Deneb, which is about 2,600 light-years away, it would be invisible to the naked eye, while Deneb would still shine brightly because of its extreme luminosity. When you look carefully at the stars on a clear night, you can notice that they have different colors. Betelgeuse in Orion glows with a reddish hue. Rigel shines blue-white. Capella appears yellow, and Antares radiates a deep orange-red. These colors are not illusions, but genuine differences in the star's surface temperatures. The hottest stars emit most of their light at shorter wavelengths, appearing blue. Cooler stars emit more light at longer wavelengths, appearing red. Our Sun, with its yellow-white, with its color, sits somewhere in the middle of this temperature range. The human eye is not very sensitive to these color differences because stars are point sources of light, but long exposure photographs clearly reveal the beautiful variety of stellar hues painting the cosmos. Stars are rarely born alone. When a giant molecular cloud collapses, it usually fragments into dozens, hundreds, or even thousands of smaller cores, each of which becomes a star. These stars are born close together in groups called star clusters. Open clusters, like the Pleiades, contain hundreds to thousands of relatively young stars that are loosely gravitationally bound. Globular clusters are much older and more tightly packed, containing hundreds of thousands of ancient stars in a spherical arrangement. Over time, many stars escape from their birth clusters due to gravitational interactions, becoming isolated field stars like our Sun. However, the fact that they form together means that all stars in a cluster have approximately the same age and chemical composition, making clusters valuable laboratories for studying stellar evolution. Many stars do not travel through space alone, but are gravitationally bound to companion stars in binary or multiple star systems. Studies suggest that more than half of all stars are part of binary or multiple systems. In a binary system, two stars orbit their common center of mass, held together by gravity. Sometimes the stars are widely separated and orbit slowly over thousands of years. Other times they are so close that they orbit each other in mere hours or days. Binary stars can exchange material, affecting each other's evolution in complex ways. The study of binary stars has taught us much about stellar masses because the orbital motion of binary stars allows us to calculate their masses using Newton's laws of gravitation. When binary stars are oriented so that we view their orbit edge-on from Earth, the stars periodically pass in front of each other as seen from our perspective. These are called eclipsing binary stars. When the brighter star passes behind the dimmer one, the total brightness of the system decreases noticeably. By carefully studying these eclipses and measuring how the brightness changes over time, astronomers can determine the sizes of the stars, their temperatures, and other properties that would be impossible to measure for single stars. The most famous eclipsing binary is Algol in the constellation Perseus, whose brightness varies noticeably over a period of less than 3 days as its two component stars eclipse each other. In close binary systems, one star can siphon matter from its companion through a process called accretion. This often happens when one star has evolved into a compact object like a white dwarf, neutron star, or black hole. As the normal star expands during its red giant phase, material from its outer layers can be captured by the compact companion's strong gravity. This material forms an accretion disk around the compact object, spiraling inward and heating to extreme temperatures. The accretion process releases tremendous amounts of energy in the form of X-rays and other high-energy radiation. These X-ray binary systems are among the brightest X-ray sources in the sky, and provide unique laboratories for studying matter under extreme conditions. Not all stars shine steadily. Variable stars change in brightness over time, sometimes predictably and sometimes erratically. There are many types of variable stars. Pulsating variables, like Cepheid variables, expand and contract rhythmically, changing their brightness as their size and surface temperature oscillate. Eclipsing binaries vary because of geometric effects as one star passes in front of the other. eruptive variables undergo sudden outbursts. The study of variable stars has been crucial to astronomy. Cepheid variables, in particular, have a relationship between their pulsation period and their intrinsic luminosity, making them excellent standard candles for measuring distances to remote galaxies. By observing how long a cepheid takes to complete one pulsation cycle, astronomers can determine its true luminosity and thus calculate its distance. About 1,350 light-years away in the constellation Orion, there lies one of the nearest and most active star-forming regions visible from Earth. The Orion Nebula is a vast cloud of gas and dust where stars are being born right now. Through telescopes, astronomers have observed thousands of young stars and protostars within this nebula, ranging from massive hot stars to tiny brown dwarfs. The nebula glows with a characteristic reddish color because the ultraviolet light from newly formed hot stars excites the surrounding hydrogen gas, causing it to emit light. In the heart of the nebula lies the trapezium, a tight cluster of 4 bright stars that illuminate the entire region. On a clear night, you can see the Orion Nebula with your naked eye as a faint fuzzy patch in Orion's sword, just below his belt. As stars form from collapsing clouds, they are often surrounded by rotating disks of gas and dust called protoplanetary disks. Within these disks, dust particles collide and stick together, gradually growing into larger and larger objects. Over millions of years, these objects accumulate enough mass to become planets. The process is complex, involving gravitational interactions, collisions, and migration of forming planets through the disk. Observations have revealed protoplanetary disks around many young stars, and we have now discovered thousands of exoplanets orbiting other stars, confirming that planet formation is a common outcome of star formation. Our own solar system formed this way about 4.5 billion years ago from a disk surrounding the young sun. Neutron stars represent matter in one of its most extreme states. When the core of a massive star collapses during a supernova, protons and electrons are squeezed together so tightly that they merge to form neutrons. The result is a neutron star, an object typically about 20 kilometers in diameter, but containing more mass than our entire sun. This means a neutron star has a density comparable to that of an atomic nucleus. A single teaspoon of neutron star material would weigh about 1 trillion kilograms on Earth. The surface gravity on a neutron star is about 200 billion times stronger than Earth's. If you dropped an object from 1 meter above the surface, it would hit the ground at a significant fraction of the speed of light. Some neutron stars emit beams of radiation from their magnetic poles, and as the neutron star rotates, these beams sweep across space like a lighthouse beacon. If one of these beams points toward Earth, we detect regular pulses of radiation as the beam sweeps past us with each rotation. These objects are called pulsars. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell, and its regular pulses were so precise that astronomers initially wondered if they might be signals from an alien civilization. We now know of thousands of pulsars, some of which rotate hundreds of times per second. These millisecond pulsars are among the most precise clocks in the universe, rivaling the best atomic clocks made by humans in their regularity. When a star more massive than about 20 times the mass of our Sun reaches the end of its life, not even neutron degeneracy pressure can stop the collapse of its core. The core continues to shrink until it becomes a black hole, a region of space where gravity is so strong that nothing, not even light, can escape from within a boundary called the event horizon. Black holes are not vacuum cleaners that suck everything in their vicinity into oblivion. They only exert gravitational influence proportional to their mass, just like any other object. However, if you were to cross the event horizon of a black hole, you would be unable to escape. And from the perspective of a distant observer, you would appear to freeze at the horizon, your light becoming increasingly red-shifted until you faded from view forever. Unlike the solid Earth or liquid water, stars are made of plasma, sometimes called the fourth state of matter. In plasma, temperatures are so high that electrons are stripped away from their atoms, creating a sea of free electrons and positively charged ions. The Sun and all stars exist in this state. Plasma behaves differently from ordinary gases because the charged particles interact strongly with electric and magnetic fields. This is why stars have complex magnetic fields that can produce sunspots, stellar flares, and other phenomena. The plasma in stars is dense enough to be opaque to most radiation, which is why photons take so long to escape from the core where they are created. Stars are not uniform throughout, but have distinct layers with different properties. In the core, temperatures and pressures are high enough for nuclear fusion. Surrounding the core is the radiative zone, where energy travels outward through the emission and absorption of photons. Above that is the convective zone, where hot plasma rises, cools, and sinks in convection currents similar to boiling water. The Sun's outer layer, called the photosphere, is what we see as the surface, though there is no true solid surface. Above the photosphere is the chromosphere, a thin layer visible during solar eclipses, and beyond that is the corona, the Sun's extremely hot outer atmosphere that extends millions of kilometers into space. Different stars have these layers in different proportions depending on their mass and temperature. At the center of our Sun, where fusion occurs, the temperature reaches about 15 million degrees Kelvin. At these temperatures, matter exists in a state completely foreign to our everyday experience. Atoms are stripped of all their electrons, and the remaining nuclei move at tremendous speeds. The pressure at the core is about 250 billion times Earth's atmospheric pressure at sea level. Under these extreme conditions, hydrogen nuclei overcome their mutual electrical repulsion and fuse together. The energy released by fusion creates an outward pressure that balances the inward pull of gravity, keeping the Sun stable. If fusion were to suddenly stop, the Sun would collapse under its own gravity in mere minutes, though there is no danger of this happening for billions of years. When we look at constellations in the night sky, it appears that the stars in each constellation are related to each other. However, Constellations are simply patterns as seen from Earth. The stars in a constellation are generally at vastly different distances from us and have no physical connection to each other. For example, in the constellation Orion, Betelgeuse lies somewhere between 500 and 600 light-years away, while Bellatrix is about 250 light-years away. They only appear to be neighbors because they happen to lie in roughly the same direction as seen from Earth. If we could travel to a distant star system and look back, the familiar constellations would disappear, replaced by entirely new patterns in the sky. Because of the inverse square law, even the most luminous stars become invisibly faint at great distances. While a supergiant star like Deneb can be seen from Earth at a distance of about 2,600 light-years, there are countless similar stars beyond that distance that we cannot see without powerful telescopes. The farthest individual stars that can be resolved by the Hubble Space Telescope are millions of light-years away, but only because they are extraordinarily luminous supergiants. The vast majority of stars in the universe are too faint and too distant for us to see individually. When we look at distant galaxies, we see not individual stars, but the combined light of billions of stars merged into a soft glow. Stars are not fixed in the sky, but are in constant motion through space. Our Sun, along with the entire solar system, is traveling through the Milky Way at about 220 kilometers per second, completing one orbit around the galactic center every 225 million years. This is sometimes called a galactic year. Other stars are moving at different speeds and in different directions. Over thousands of years, these motions cause the constellations to slowly change shape. The Big Dipper, for example, looked different 50,000 years ago and will look different 50,000 years in the future. Astronomers can measure these stellar motions using precise positional measurements and Doppler shifts of stellar spectral lines. Just as the pitch of an ambulance siren changes as it passes you, the wavelength of light from a star changes if the star is moving toward or away from us. This is called the Doppler effect. If a star is moving toward us, its light is compressed to shorter wavelengths, shifting toward the blue end of the spectrum, a phenomenon called blue shift. If a star is moving away, its light is stretched to longer wavelengths, shifting toward the red, called redshift. By carefully measuring these shifts in the spectral lines of a star's light, astronomers can determine its radial velocity, how fast it is moving toward or away from us. This technique has been crucial for discovering exoplanets, as an orbiting planet causes its star to wobble slightly, producing periodic Doppler shifts in the star's spectrum. Like Earth, stars have magnetic fields generated by the motion of charged particles in their interiors. The Sun's magnetic field is created by the complex motions of plasma in its convection zone. This field is not uniform, but is tangled and twisted, creating active regions where the field lines emerge through the surface. Sunspots appear in these regions. They are cooler areas on the Sun's surface where concentrated magnetic fields inhibit convection. The Sun's magnetic field reverses polarity approximately every 11 years as part of the solar cycle. More massive and more rapidly rotating stars can have much stronger magnetic fields than the Sun, leading to more dramatic stellar activity. Occasionally, the tangled magnetic fields on the Sun suddenly rearrange themselves in a process called magnetic reconnection. This releases enormous amounts of energy in an explosive event called a solar flare. A large solar flare can release as much energy as millions of nuclear bombs exploding simultaneously. The energy heats plasma to tens of millions of degrees and accelerates particles to nearly the speed of light. These particles and associated radiation can affect Earth's magnetic field and atmosphere, creating auroras and potentially disrupting satellites and power grids. Other stars also produce flares, and some stars undergo superflares far more powerful than anything the Sun has produced in recorded history. One of the enduring mysteries of solar physics is the coronal heating problem. The Sun's visible surface, the photosphere, has a temperature of about 6,000 degrees Kelvin. However, the corona, the Sun's outer atmosphere visible during solar eclipses, has a temperature of over 1 million degrees Kelvin. This violates our intuition that things should get cooler as you move away from a heat source. The exact mechanism that heats the corona is still not fully understood, though current theories suggest it likely involves the dissipation of magnetic energy through various processes, including magnetic reconnection and wave heating. Similar coronal heating has been detected around other stars, suggesting it is a common stellar phenomenon. In addition to light, stars produce enormous numbers of tiny particles called neutrinos. Neutrinos are created during fusion reactions in the core of stars. Unlike photons, which interact strongly with matter and take thousands of years to escape a star, neutrinos barely interact with anything. They pass straight through the star at nearly the speed of light, escaping in mere seconds. Billions of neutrinos from the Sun pass through your body every second, but they are so weakly interacting that you never notice. Detecting these solar neutrinos was a major challenge for physicists, but specialized detectors located deep underground have successfully measured them, providing direct evidence that fusion is occurring in the Sun's core. In astronomy, any element heavier than helium is called a metal, regardless of its actual chemical properties. The metallicity of a star refers to the abundance of these heavier elements in its composition. The very first stars in the universe, formed from primordial hydrogen and helium, had zero metallicity. As these stars died and enriched the interstellar medium with heavy elements, subsequent generations of stars were born with progressively higher metallicities. Metallicity affects many aspects of stellar evolution, including the star's opacity, which influences its structure and lifetime. It also affects planet formation. Planets require heavy elements to form, so stars with higher metallicity are more likely to have planetary systems. Astronomers classify stars into different populations based on their age and metallicity. Population 1 stars are relatively young, metal-rich stars like our Sun that formed relatively recently from gas enriched by previous generations of stars. They are typically found in the disk of spiral galaxies. Population 2 stars are older, metal-poor stars that formed earlier in the history of the universe. They are found in globular clusters and in the halos of galaxies. Astronomers theorize there may also be population 3 stars. a hypothetical first generation of stars formed from pristine primordial gas, though none have been definitively identified. Based on models, these first stars likely would have been very massive and lived brief lives, seeding the universe with the first heavy elements. The stars we see today are not made purely of primordial hydrogen and helium. They contain heavy elements created in earlier generations of stars that lived, died, and returned their material to the interstellar medium. Our Sun, which is about 4.5 billion years old, formed from a cloud that had been enriched by countless previous stellar cycles. The heavier elements in the Sun, including the metals that would later form planets like Earth, were created in stars that exploded billions of years ago. In a very real sense, we are all made of stardust, composed of atoms that were forged in stellar cores and scattered across the galaxy by supernovae and stellar winds. Before a star settles onto the main sequence, it goes through a phase called the T Tauri stage, named after the prototype star T Tauri. These are pre-main sequence stars that are still contracting and have not yet begun stable hydrogen fusion. T Tauri stars are characterized by strong stellar winds, irregular variability in brightness, and often by the presence of a protoplanetary disk. They are typically found in or near star-forming regions. The T Tauri phase lasts about 10 million years before the star settles onto the main sequence. During this time, the star's brightness and temperature fluctuate as it adjusts to its new life as a hydrogen-burning star. Our Sun went through a T Tauri phase about 4.5 billion years ago. Sunspots are cool, dark regions on the Sun's surface caused by concentrated magnetic fields. They appear dark because they are cooler than the surrounding photosphere, though they are still extremely hot by earthly standards. Sunspots come and go over days to weeks, and the number of sunspots visible on the Sun varies with the 11-year solar cycle. Other stars also have star spots similar to sunspots. By watching how a star's brightness changes as it rotates, and these spots come in and out of view, astronomers can study the star's rotation period and the characteristics of its magnetic field. Some stars have much more extensive spot coverage than the Sun, suggesting they have more intense magnetic activity. Main sequence stars span an enormous range of sizes and luminosities. The most massive main sequence stars can be hundreds of thousands of times more luminous than our Sun and have masses of more than 100 solar masses. They are large, hot, and blue. The least massive main sequence stars are red dwarfs, with only about 8% of the Sun's mass. They are small, cool, and dim, emitting only about 1/1000th the light of our Sun. Between these extremes lies a continuous sequence of stars of every intermediate size. This diversity is one of the most beautiful aspects of stellar astronomy, revealing that nature creates stars in virtually every possible configuration allowed by the laws of physics. One of the most important tools in astronomy is the Hertzsprung-Russell diagram, or HR diagram. This is a graph that plots stars' luminosities versus their temperatures, or colors. When many stars are plotted on an HR diagram, they fall into distinct regions. Most stars lie along a diagonal band called the main sequence, where stars spend most of their lives fusing hydrogen. Giants and supergiants occupy the upper right region, being cool but luminous. White dwarfs occupy the lower left, being hot but dim. By plotting a star on an HR diagram, astronomers can immediately understand its stage of evolution, estimate its mass, and predict its future. The HR diagram is to stellar astronomy what the periodic table is to chemistry, an organizing framework that reveals deep patterns. Globular clusters are spherical collections of hundreds of thousands to millions of stars. Tightly bound by gravity into a compact ball typically 50 to 100 light-years across. These clusters orbit in the halos of galaxies and contain some of the oldest stars in the universe, with ages often exceeding 12 billion years. The stars in globular clusters are almost all population 2 stars, metal poor and formed in the early universe. Because all the stars in a cluster formed at approximately the same time from the same gas cloud, globular clusters provide valuable laboratories for studying stellar evolution. By plotting an HR diagram for a globular cluster, astronomers can see stars at different stages of evolution all at once, like a snapshot of an entire stellar population. Open clusters are groups of stars that are more loosely bound than globular clusters, typically containing hundreds to a few thousand stars spread over tens of light years. These clusters are generally younger than globular clusters, with ages ranging from a few million to a few billion years. Famous examples include the Pleiades and the Hyades in the constellation Taurus. Stars in open clusters gradually escape over time due to gravitational interactions. So many open clusters are only temporary, dispersing into the general stellar population after a few 100 million years. Our Sun probably formed in an open cluster about 4.5 billion years ago, but its siblings have long since scattered throughout the galaxy. Within a star cluster, where all the stars formed at the same time, the massive stars evolve much faster than the less massive ones. After just a few million years, the most massive stars in a cluster will have already left the main sequence and exploded as supernovae, while lower mass stars are still peacefully fusing hydrogen. This creates a pattern on the HR diagram where the upper main sequence is progressively depleted in older clusters. By observing which types of stars have already left the main sequence, astronomers can estimate the age of a star cluster. This technique, called main sequence turn-off dating, has been used to determine that some globular clusters are among the oldest objects in the universe, where starlight is spread out into a spectrum. It reveals dark absorption lines at specific wavelengths. These lines are caused by atoms in the star's atmosphere absorbing light at characteristic wavelengths. Each chemical element produces a unique pattern of spectral lines, like a fingerprint. By studying these patterns, astronomers can determine what elements are present in a star and in what quantities. This technique, called spectroscopy, has revealed that stars are made primarily of hydrogen and helium, with only about 2% heavier elements. Spectroscopy also reveals a star's temperature, pressure, rotation rate, and magnetic field strength. Nearly everything we know about the physical properties of stars comes from analyzing their spectra. The very first stars in the universe formed from gas that was almost entirely hydrogen and helium, the elements created in the Big Bang. These hypothetical population 3 stars would have been very different from modern stars. Without heavier elements to increase opacity and cooling, they might have been able to grow much more massive than current stars, perhaps reaching thousands of solar masses. They would have lived brief, intense lives before exploding, as the first supernovae, seeding the universe with its first heavy elements. Despite decades of searching, astronomers have not yet definitively identified any population 3 stars, though they may have detected their chemical signatures in extremely metal-poor stars that formed from gas enriched by just 1 or 2 previous supernovae. Most stars, including our Sun, have more oxygen than carbon in their atmospheres. However, some evolved stars have undergone processes that increase their carbon abundance until they have more carbon than oxygen. These are called carbon stars, and they have distinctive red colors and spectral features. The extra carbon was created by helium fusion in the star's interior and brought to the surface by convection. Carbon stars are cool giants or supergiants in late stages of evolution. They produce substantial amounts of carbon-rich dust in their stellar winds, and this dust contributes to the formation of carbon-rich materials in the interstellar medium. Carbon stars played an important role in enriching the early universe with carbon, an element essential for life as we know it. Wolf-Rayet stars are a rare class of evolved massive stars with surface temperatures exceeding 30,000 degrees Kelvin. They have lost their outer hydrogen envelopes through powerful stellar winds, exposing deeper layers enriched in helium, carbon, nitrogen, and oxygen. These stars emit intense ultraviolet radiation and have stellar winds with speeds reaching several thousand kilometers per second, losing mass at prodigious rates. Wolf-Rayet stars represent a brief phase in the lives of the most massive stars, occurring after they have exhausted the hydrogen in their cores, but before they explode as supernovae. They are important sources of heavy elements and energy in their host galaxies. While many stars exhibit variability, some stars, including our Sun, maintain remarkably stable luminosities over long timescales. The Sun's luminosity has varied by less than 1% over the last several billion years. This stability is crucial for the development of life on Earth, as large variations in the Sun's output would dramatically affect Earth's climate. However, even stable stars like the Sun are not perfectly constant. The Sun undergoes an 11-year activity cycle, during which its brightness varies by about 0.1%. And individual active regions can cause variations of a few tenths of a percent over days to weeks. On human timescales, these variations are small enough that they do not significantly affect Earth's climate, but they can be detected with sensitive instruments. When a Sun-like star reaches the end of its red giant phase, it gently expels its outer layers into space, creating an expanding shell of glowing gas called a planetary nebula. The name is misleading. These objects have nothing to do with planets. They were named by 18th century astronomers who thought they looked like planets through their small telescopes. At the center of each planetary nebula is the hot, exposed core of the former red giant, now a white dwarf. The ultraviolet radiation from this white dwarf causes the surrounding gas to fluoresce, creating beautiful, colorful structures. Planetary nebulae last only about 10,000 years before fading away, but they play an important role in enriching the interstellar medium with elements created in the star. In the year 1054 CE, Chinese and Arab astronomers recorded the appearance of a brilliant guest star in the constellation Taurus. This was actually a supernova explosion, the death of a massive star. Today, at that position, we see the Crab Nebula, an expanding cloud of gas still glowing from the energy of that ancient explosion. At its center lies a pulsar, a rapidly rotating neutron star that spins about 30 times per second. The Crab Nebula is one of the most studied objects in astronomy and has provided crucial insights into supernova explosions and neutron stars. The nebula is still expanding at about 1,500 kilometers per second, and it will continue to grow and fade over the coming millennia. Asymptotic giant branch stars, or AGB stars, are evolved low to intermediate mass stars that have exhausted the helium in their cores and now burn helium and hydrogen in thin shells around an inert carbon-oxygen core. These stars experience periodic thermal pulses, brief episodes where the helium-burning shell suddenly becomes very active, causing the star's luminosity to increase and its outer layers to expand even further. During these pulses, convection can bring material from deep inside the star to the surface, a process called dredge-up. This exposes carbon and other elements created by fusion, changing the star's surface composition. These episodes also enhance the star's mass loss rate, contributing to the eventual formation of a planetary nebula. AGB stars are the primary source of carbon and many other elements in the universe. Mira variables are pulsating red giant stars that vary in brightness over periods of months to years. The prototype Mira in the constellation Cetus varies from magnitude 2, easily visible to the naked eye, to magnitude 10, requiring a telescope, over a period of about 11 months. During this cycle, the star's radius changes by about 25% and its surface temperature fluctuates. These dramatic variations occur because the star is unstable, with its outer layers pulsating in and out. Mira variables are cool, evolved stars near the end of their lives, and their pulsations may help drive strong stellar winds that will eventually expel their outer envelopes completely. Sirius, the brightest star in our night sky, is actually a binary star system. The bright star we see, Sirius A, is a hot, luminous main sequence star about twice the mass of the Sun. But orbiting around it is Sirius B, a white dwarf about the same mass as our Sun, but compressed to about the size of Earth. Sirius B was discovered in 1862 by Alvan Clark, making it one of the first white dwarfs ever detected. The two stars orbit each other every 50 years. Sirius B is extremely faint compared to Sirius A, making it difficult to observe directly because of the glare from its brilliant companion. This system provides valuable insights into stellar evolution and the ultimate fate of sun-like stars. While the vast distances between stars can seem incomprehensibly large, some stars are relatively nearby. Proxima Centauri, the closest star to our solar system, is about 4.2 light-years away. Alpha Centauri A and B, a binary system, are slightly farther at about 4.4 light-years. Within 10 light-years of Earth, there are only about a dozen known star systems, and most of these are dim red dwarfs invisible to the naked eye. Within 100 light-years, there are thousands of stars, including many familiar ones like Sirius, Vega, and Arcturus. These nearby stars allow astronomers to make precise measurements that would be impossible for more distant stars, including detailed studies of their masses, radii, and planetary systems. Betelgeuse, the red supergiant marking Orion's shoulder, is one of the most famous stars in the sky. It is a massive star, with estimates suggesting perhaps 15 to 20 times the mass of the Sun, and it has already exhausted the hydrogen in its core. Now burning helium and heavier elements in its interior, Betelgeuse has swollen to enormous size, large enough that if placed at the center of our solar system, its surface would extend beyond the orbit of Mars. Betelgeuse is nearing the end of its life, and astronomers estimate it will explode as a supernova sometime in the next 100,000 years, though the exact timing remains uncertain. When it does, it will briefly become one of the brightest objects in the sky, possibly visible even during the day. For a few weeks, it will outshine the moon before gradually fading from view. The chemical composition of stars varies depending on where they are located in the galaxy. Stars near the center of the Milky Way tend to have higher metallicities because the galactic center has been enriched by many generations of stars. Stars in the outer regions of the galaxy tend to be more metal poor because star formation has been less intense there. Globular clusters in the galactic halo contain very metal poor stars, reflecting their formation in the early universe. These abundance patterns help astronomers understand the history of star formation and chemical enrichment across the galaxy. They also provide clues about the Milky Way's formation and evolution over its 13 billion-year history. Many stars are surrounded by disks of gas and dust, either protoplanetary disks around young stars or debris disks around older stars. Protoplanetary disks contain the material from which planets form. Observations have revealed complex structures in these disks, including gaps carved by forming planets, warps, and spirals. Debris disks are composed of dust and small bodies left over after planet formation is complete. They are analogous to the Kuiper belt and asteroid belt in our solar system, but can be much more extensive. The study of these disks provides insights into planet formation and the early history of planetary systems. The presence of gaps or other structures in disks often indicates the presence of planets, even if the planets themselves cannot be directly detected. In the dense cores of globular clusters, where hundreds of thousands of stars are packed into a small volume, stellar collisions and close encounters are more likely. These interactions can produce exotic objects called blue stragglers, which appear younger and bluer than other cluster members. Blue stragglers may form when two stars merge, creating a more massive star that appears to be on the main sequence, even though it should have already evolved off. Stellar collisions and interactions can also lead to the formation of binary systems, the ejection of stars from clusters, and other complex dynamical phenomena. In very dense environments, these interactions play an important role in shaping the evolution of the stellar population. Cepheid variable stars pulsate regularly with periods ranging from days to months. In the early 20th century, Henrietta Swan Leavitt discovered that there is a relationship between a Cepheid's pulsation period and its intrinsic luminosity. More luminous Cepheids have longer periods. This period luminosity relationship makes Cepheids invaluable as standard candles for measuring astronomical distances. By observing a Cepheid's pulsation period, astronomers can determine its true luminosity. By comparing this to its apparent brightness, they can calculate its distance using the inverse square law. This technique allowed Edwin Hubble to measure the distances to nearby galaxies and discover that the universe is expanding. Cepheids remain one of the most important tools for determining cosmic distances. RR Lyrae stars are similar to Cepheid variables, but are older, less massive, and less luminous. They are pulsating, horizontal branch stars found primarily in globular clusters. RR Lyrae stars all have approximately the same intrinsic luminosity, making them useful standard candles for measuring distances to globular clusters and nearby galaxies. Because they are population 2 stars, RR Lyrae are particularly useful for studying the structure of the Milky Way's halo and the distances to ancient stellar populations. Their predictable luminosities and their presence in globular clusters make them valuable tools for understanding the distribution and ages of old stars in our galaxy and beyond. About 5 billion years from now, the Sun will exhaust the hydrogen in its core. When this happens, it will begin to evolve off the main sequence, expanding into a red giant. The Sun's outer layers will swell to perhaps 100 times their current size, possibly engulfing the orbits of Mercury and Venus and dramatically heating Earth. During this phase, the Sun will fuse helium in its core and hydrogen in a shell around the core. After about 1 billion years as a red giant, the Sun will shed its outer layers in a planetary nebula, leaving behind a white dwarf remnant about the size of Earth, but containing about half the Sun's current mass. This white dwarf will slowly cool over trillions of years, eventually fading to a black dwarf, a cold, dark ember of the once brilliant Sun. Throughout their lives, stars continuously lose mass through stellar winds, streams of particles flowing outward from their surfaces. In main sequence, stars like the Sun, this mass loss is relatively modest, amounting to about 1 part in 10 trillion of the star's mass per year. However, in evolved stars like red giants and supergiants, mass loss rates can be dramatically higher, sometimes reaching 1 part in 100,000 per year or more. These intense winds can remove significant fractions of a star's mass, altering its evolution and contributing to the enrichment of the interstellar medium. The mass lost by stars through stellar winds returns to the interstellar gas and dust from which future generations of stars will form, continuing the cycle of stellar death and rebirth. Luminous blue variables, or LBVs, are among the most luminous and massive stars known. They are hot, blue supergiants that exhibit dramatic variability in brightness and periodic outbursts where they eject large amounts of material. During these outbursts, an LBV can brighten by several magnitudes and lose mass equivalent to several Earths. The most famous example is Aetial Carinae, which underwent a giant outburst in the 1840s and remains one of the most luminous stars in the Milky Way. LBVs are thought to be in a brief evolutionary phase preceding the transition to Wolf-Rayet stars. They are important for understanding the final stages of massive star evolution and the mechanisms that allow stars to lose large amounts of mass before exploding as supernovae. The Pleiades, also known as the Seven Sisters, is one of the most beautiful and well-known open clusters in the sky. Visible to the naked eye as a tight group of stars in the constellation Taurus, the cluster contains hundreds of stars, though only 6 or 7 are typically visible without a telescope. The Pleiades formed about 100 million years ago, making them relatively young in astronomical terms. The stars are still surrounded by remnants of the gas and dust from which they formed, visible as faint reflection nebulosity in long-exposure photographs. The brightest stars in the Pleiades are hot, blue B-type stars, and the cluster is a favorite target for both amateur and professional astronomers. In very close binary systems, the two stars can actually come into contact, sharing a common envelope of gas. These contact binaries eventually merge, combining into a single, more massive star. The merger process releases tremendous amounts of energy and can create exotic objects or trigger outbursts. Stellar mergers are thought to be responsible for certain types of transient events observed in the sky, including some novae and possibly some supernovae. The merged star may appear younger than surrounding stars of similar mass because it has been rejuvenated by the merger, giving it fresh hydrogen to burn. These mergers complicate our understanding of stellar evolution, but also provide natural laboratories for studying matter under extreme conditions. Star formation is not just a process from the distant past, but continues in our galaxy today. The Milky Way forms approximately 3 to 7 new stars every year. Most star formation occurs in the spiral arms, where giant molecular clouds are compressed by spiral density waves, triggering the collapse of gas and dust. Active star-forming regions like the Orion Nebula, the Eagle Nebula, and the Carina Nebula contain thousands of young stars and protostars. By studying these nearby stellar nurseries, astronomers can observe the star formation process in action and understand how stars like our Sun came to be billions of years ago. Stars do not exist in isolation, but profoundly influence their environments. The radiation from hot, massive stars heats and ionizes surrounding gas, creating emission nebulae. Stellar winds and supernova explosions push material away, creating shells and bubbles in the interstellar medium. The pressure from these winds and explosions can trigger the collapse of nearby clouds, initiating new rounds of star formation. Stars also inject heavy elements into their surroundings, gradually enriching the interstellar medium. Over millions of years, multiple generations of stars shape the structure and composition of galaxies. The interplay between stars and their environment is a fundamental process in galactic evolution, determining where and when new stars will form. The scientific study of stars is called stellar astronomy or stellar astrophysics. This field encompasses understanding how stars form, how they generate energy, how they evolve over time, and how they die. Stellar astronomers use observations across the electromagnetic spectrum, from radio waves to gamma rays, to study stars at different stages of their lives. They also use theoretical models and computer simulations to understand the physics occurring deep inside stars, where direct observation is impossible. The field has made tremendous progress over the past century, transforming stars from mysterious lights in the sky to well-understood objects whose properties and behaviors can be predicted with remarkable accuracy. For thousands of years before the development of modern astronomy, human cultures around the world created myths and legends about stars and constellations. The ancient Greeks saw heroes, monsters, and gods in the patterns of stars. Chinese astronomers developed sophisticated systems for tracking and interpreting celestial phenomena. Indigenous Australian cultures created complex oral traditions connecting stars to creation stories and navigation. These myths reflect humanity's deep connection to the night sky and our drive to find meaning in the cosmos. While modern astronomy has revealed the true nature of stars as distant suns, the beauty and wonder that inspired these ancient stories remain with us, reminding us of our place in the vast universe. Our home galaxy, the Milky Way, contains an estimated 200 to 400 billion stars. These stars span the full range of masses, temperatures, and evolutionary stages. The vast majority are dim red dwarfs that cannot be seen with the naked eye. But the galaxy also contains everything from newborn protostars to ancient white dwarfs, from ordinary main sequence stars to massive supergiants on the verge of explosion. When you look at the Milky Way stretched across a dark sky, you are seeing the combined light of countless suns, each one a world unto itself, many perhaps surrounded by their own families of planets. The Milky Way is just one galaxy among hundreds of billions in the observable universe, suggesting that the total number of stars in the cosmos is almost beyond comprehension. While most stars are designated by catalog numbers, many bright stars have traditional names that have been used for centuries or millennia. These names come from various cultural traditions, primarily Arabic, Greek, and Latin. Betelgeuse derives from an Arabic phrase meaning the hand of Orion. Sirius comes from the Greek word for glowing or scorching. Aldebaran, the bright red star in Sao. Taurus means the follower in Arabic, referring to how it follows the Pleiades across the sky. In 2016, the International Astronomical Union began formally approving official names for stars, preserving these ancient names and adding new ones. These traditional names connect us to the astronomers and stargazers of past civilizations, who also looked up in wonder at the same lights in the night sky. The discovery of exoplanets has revealed that planetary systems can be very different from our own. Some planets orbit extremely close to their stars, completing one orbit in less than a day. These hot Jupiters are giant planets that, based on current models, likely migrated inward from their formation locations farther out in their systems. Other planets orbit very far from their stars, taking hundreds or thousands of years to complete one orbit. Some planets are in highly elliptical orbits that bring them alternately very close to and very far from their stars. A few planets have even been discovered orbiting binary stars, experiencing 2 sunrises and sunsets each day, like Tatooine in Star Wars. These diverse planetary systems show that planet formation is a complex and varied process. Some stars in our galaxy are nearly as old as the universe itself. By studying these ancient stars, astronomers can learn about conditions in the early universe, a field called stellar archaeology. The most metal-poor stars, with almost no elements heavier than helium, formed from gas enriched by only 1 or 2 previous supernovae. Their chemical compositions provide clues about the properties of the very first stars and the first supernovae. Some ancient stars show unusual abundance patterns that could suggest enrichment by exotic events, like pair instability supernovae or the collisions of neutron stars, though confirming these scenarios requires further study. These stellar fossils are precious because they carry information about an era when the universe was very different from today. For thousands of years, humans have used stars for navigation. Because stars rise and set at predictable times and their positions change in regular patterns throughout the year, they provide reliable references for determining direction and time. Polaris, the North Star, appears almost stationary in the northern sky, making it invaluable for finding north in the northern hemisphere. Sailors used the positions of stars above the horizon to determine their latitude. The Polynesian people developed sophisticated techniques for navigating across the Pacific Ocean using stars, along with waves and bird behavior. Even today, astronauts learn celestial navigation as a backup method in case their electronic systems fail. The stars that guided ancient mariners continue to shine, eternal beacons in the sky. The most distant individual stars that have been observed are millions of light years away. These extremely distant stars are only visible because they are extraordinarily luminous supergiants, sometimes temporarily brightened further by gravitational lensing from foreground galaxies. One remarkable example detected in 2018 was a blue supergiant star temporarily magnified by gravitational lensing, allowing astronomers to see it at a distance of about 9 billion light-years. Even more distant stars exist, but they are too faint to detect individually. When we observe very distant galaxies, we see not individual stars, but the integrated light of billions of stars merged together. The study of these distant stars and galaxies allows us to look back in time and observe the universe as it was billions of years ago. Stars are not just distant lights, but are fundamental to our very existence. The atoms in our bodies were created in stars and scattered into space by stellar winds and supernova explosions. The sun provides the energy that drives Earth's weather, ocean currents, and ultimately all life through photosynthesis. Without stars, there would be no heavy elements, no planets, no life. Every breath we take contains oxygen forged in massive stars billions of years ago. The calcium in our bones, the iron in our blood, the carbon in our cells, all were created in stellar furnaces and delivered to us by stellar deaths. In the most literal sense, we are children of the stars, born from stellar ashes and warmed by stellar light. Even within a single evolutionary stage, stars can have very different timescales. A massive star might spend only a few million years on the main sequence, while a red dwarf can spend trillions of years there. After leaving the main sequence, a star like the Sun will spend about 1 billion years as a red giant. But more massive stars pass through their giant phases in just a few 100,000 years. The helium-burning phase is much shorter than the hydrogen-burning phase, lasting perhaps 1/10 as long. The final stages of massive stars proceed with breathtaking speed. Carbon burning lasts about 1,000 years, oxygen burning about a year, and silicon burning just a day before the core collapses. These vast differences in timescales reflect the different internal pressures and temperatures in stars of different masses. Our Sun is approximately 4.5 billion years old, meaning it is about halfway through its main sequence lifetime. It has been steadily fusing hydrogen into helium in its core for all this time, and it will continue to do so for another 5 billion years. The Sun has actually grown slightly brighter over its lifetime, with its luminosity having increased by about 30% since it first reached the main sequence. This gradual brightening will continue, which has implications for Earth's future climate. Based on climate models, in about 1 billion years, the increased solar luminosity will make Earth's surface too hot for liquid water to exist, effectively ending the habitable period for life as we know it, even though the Sun won't become a red giant for another 4 billion years after that. Stars are natural laboratories where matter exists under conditions impossible to reproduce on Earth. The cores of stars reach temperatures of millions of degrees and pressures billions of times Earth's atmospheric pressure. Neutron stars have magnetic fields trillions of times stronger than any magnet we can create. By studying stars, physicists can test theories about nuclear physics, plasma physics, quantum mechanics, and general relativity. The detection of neutrinos from the Sun confirmed theories about fusion reactions. Observations of neutron stars provided evidence for the existence of neutron-degenerate matter. The study of white dwarfs helped physicists understand electron degeneracy. Every new observation of stars teaches us not just about astronomy, but about the fundamental laws of nature. When you look at a star, you are seeing it not as it is now, but as it was when its light began its journey toward Earth. The light from Sirius left that star about 8.5 years ago, while the light from Deneb left over 2,000 years ago, when ancient civilizations were building empires on Earth. In a very real sense, looking at stars is time travel, a window into the past. Yet stars also represent our future. The sun will continue to shine for billions of years, long after human civilization as we know it has passed. The red dwarfs born today will still be burning when the universe is many times its current age. Stars connect us to both the ancient past and the distant future, reminding us of our place in the great sweep of cosmic time. Perhaps the most important fact about stars is not a scientific one, but a human one. For as long as humans have existed, we have looked up at stars with wonder. They have inspired countless myths, guided travelers across oceans and deserts, and sparked questions about our place in the universe. Stars have driven our curiosity to explore, to understand, to dream of what might lie beyond our world. They remind us that we are part of something much larger than ourselves, connected to the cosmos through the very atoms of our being. The same light that illuminated the caves of our ancestors shines down on us still, and it will shine on our descendants for ages to come. In their patient, eternal glow, stars offer us perspective, humility, and hope. Good night.